This is lecture 31 of Calculus 2, and today we are going to cover the first part of section 11.2, which is about series, or sometimes called infinite series. Shall we begin? Okay, so let's start with a motivating question. Suppose I write some decimal, some infinite decimal, like 0.999999, etc. How do we understand that? Well, we understand that as 9/10 plus 9 over 100 plus 9 over 1,000 plus 9 over 10,000, etc. Okay, and we can write that in a sum notation, or a so-called sigma notation, as the sum, n goes from 1 to infinity, of 9 over 10 to the nth power. So the question I ask is, so this is an example of what is called an infinite series. Okay, so here's the formal definition. A sequence A sub n has an associated series, which is denoted sum A sub k, say k goes from 1 to infinity. So what I mean by this is A1 plus A2 plus A3, etc. Now, the question is, the real question we might have, what does it mean to take an infinite sum of numbers? So I'm going to, sometimes this would make sense. For example, in my motivating question, 0.999999, etc., makes sense as a real number, and we've rewritten that as an infinite series. But in other cases, it doesn't always make sense. For example, we might take the summation n goes from 1 to infinity, and that would be 1 plus 2 plus 3 plus 4 plus 5 plus 6. And when we add these things together, we keep adding, we get a number that's getting bigger and bigger. It becomes unbounded. It goes to infinity. So this doesn't make sense as a real number. So I want to make sense of that. And the way we make sense of that, we'll see right now. So, so what I want to do is consider the so-called, here's the definition, the nth partial sum of a series. Let's denote the indices by k now, summation ak. Now, if I don't put the indices down, I usually put the indices down, but if I don't, the assumption is k is going from 1 to infinity. So I sometimes write summation a sub k instead, without saying what k is varying over. So the nth partial sum is the expression, is the finite sum S sub n, which is A1 plus A2 plus A3 all the way up to the nth term. You could also write this as the sum k goes from 1 to n of A sub k. All right, so for example, S sub 1 is A1, S sub 2 is A1 plus A2, S sub 3 is A1 plus A2 plus A3, etc. All right, so now the nth partial sum, so these form a sequence. S sub k, or S sub n, I should say, probably. Okay, so, and I want to concentrate on that sequence. And so we're going to give a definition now about what it means for the sum to make sense, the infinite sum to make sense. So definition, the sum of the series is convergent if the limit as n goes to infinity of the nth partial sums exists. Okay, so if it equals a number s, of a real number s, we say the series converges to s. So that's the notion of convergence of an infinite series. And otherwise, if it doesn't converge, the series is said to be divergent. So that's the basic definition. So for example, we already had one. The example is the sum over n goes from 1 to infinity, diverges. Because that's 1 plus 2 plus 3 plus 4 plus 5. That just gets unbounded, okay? So what I want to talk about are just a couple of examples today. We will not complete the section. We're just going to do the first half of the section. Okay, so here's the first example of a series that I want to consider. It's called the geometric series. So it's based on the following thing. You have two real numbers, a and r. So these are real numbers that are fixed. Real numbers. This is awful handwriting. Okay, and then we look at the expression a plus a times r. We multiply the previous term by r to get ar squared, multiply by r again to get ar cubed, and etc. So this is the sum ar to the n minus 1 as n goes from 1 to infinity, or you could write it as the sum n goes from 0 to infinity of ar to the n. You could also write it like that, but let's continue to write it like the first way. Okay, so the number r is called the common ratio, and the number a is called the initial term. And the question is, does the geometric series converge for which values of a and r? And if so, what does it converge to? So I want to explain how this is going to work. So I'm going to show you how the method. Okay, so let's consider the nth partial sum, S sub n. That would be a times r plus ar squared. That would not be a times r. That would be a plus ar plus ar squared, all the way up to ar to the n minus 1, I believe. And now I'm going to take this equation and multiply it on both sides by r. So rsn is ar plus ar squared plus ar cubed, all the way up to a times r to the n. So now let's subtract the second equation from the first equation. So what do you get? You're going to get Sn minus Rsn is equal to, now every term on the first line of the first equation on the right, except the initial term a, is going to be canceling with some term on the bottom equation. So you're going to get an a, and then what's left over is a minus ar to the nth power. So now what I'm going to do is I'm going to factor out an Sn on the left side. So 1 minus r times Sn is equal, and I'm going to factor out an a on the right. So is 1 minus r to the n. And now I solve for Sn. So what does that tell me? It tells me that Sn is equal to a times 1 minus r to the n over 1 minus r. So that should be boxed off. That's an important equation. Okay, so now that's the nth partial sum. Now we have a formula for the nth partial sum, but we're trying to figure out whether the series converges. So we're going to need to know whether the limit of the sequence of the nth partial sums converges to a real number or not. So let's check that out. So when does Sn converge? That's what we're reduced to. So so what was it? We had a times 1 minus r to the n over 1 minus r. Now, there are two cases to consider. The absolute value r is less than. So cases, first case is r absolute value less than 1. Then in this case, r to the n will tend to 0. So in that case, and then the expression tends to, so then Sn tends to a times 1 minus 0 over 1 minus r. So in this case, the series converges, i.e. the summation ar to the n minus 1, n goes from 1 to infinity, we'll just write an equal sign. It's equal to a over 1 minus r. Now what happens if the absolute value of r is greater than 1? Well, in those two cases, it's not hard to check that what's left over, it's going to, if r is 1, for example, you can go back and you'll see the series doesn't converge. In fact, it diverges in all other cases. So this is the important result I wanted to indicate. All right, so let's do some examples. Okay, so here's an example. Let's consider the sum of 2 to the 2nth power times 3 to the 1 minus nth power. N goes from 1 to infinity. It looks nothing like, in this form, it doesn't look like a geometric series, but I claim it is. In fact, it's easy to check if something is a geometric series. You write out the first few terms. So the first term is 2 squared times 3 to the 0, then plus 2 to the 4th power times 3 to the 1st power, plus 2 to the 6th times 3 to the 2nd power, and so on. Now, this would be our A. And how do we get from this term to this term? We multiply by 2 squared times 3 to get from there to there. Now, in order to get from the second term to the third term, we better multiply by the same amount, and indeed, we multiply by 2 squared times 3. We get to the next term, and so on. So this is geometric, and A is 2 squared times 3 to the 0, which is 4, and R is 2 squared times 3, which is 12. So since R has absolute value bigger than 1, the series diverges. Okay, so that's an example. Here's another one. Suppose we look at the sum, n goes from 1 to infinity, of minus 1 to the n times e to the 2n. E is the the base for the natural logarithms, over 3 to the m plus first power. So let's start writing the first few terms. So it starts off as minus 1 e to the e squared over 3 squared plus e to the 4th over 3 cubed, and the next term is negative e to the 6th over 3 to the 4th, and so on. It alternates in sign. The first term, this would be our a, and going from the first term to the next term in the sum, it looks like we're multiplying by minus e squared over 3. And let's see if that's correct, because we have to go from this term to this term. E to the 4th to e to the 6th is multiplying by negative e squared over 3 again. So here the common ratio is negative e squared over 3, and a is equal to negative e squared over 3 squared, negative e squared over 9, okay? Now e squared is about 9, so it's going to be negative, this absolute value here is bigger than 1, so this series is again going to diverge. It's the second case of divergence. Okay, so let's try one more example. Let's try our 0.999999 example. Now, you're probably taught in somewhere along the line that an infinite repeating decimal of the form 0.999999 should be equal to 1. And the way we're going to understand that is to use the geometric series. So this is sum 9 over 10 to the n is going from 1 to infinity. This is geometric. The first term is 9/10. That's our a. And then you're going to 9 over 10 squared plus 9 over 10 cubed. So r is 1/10. So therefore, the value of r has absolute value less than 1. So it converges. And what does it converges to? It converges to a, which is 9/10, over 1 minus r, which is 1 minus 1/10, or in other words, 9/10 over 9/10. So we get a 1 as expected. Okay, so that's our first example that occurs. Oh, here's one more example that comes up later in the text a lot. What if we look at summation x to the n goes from 1 to infinity? You can think of that as 1 plus x squared plus x cubed. It's like an infinite polynomial in the variable x. And now let's assume the absolute value of x is less than 1. It's obviously geometric. The initial term is 1 and r is x. So it converges to, this expression converges to 1 over 1 minus x by the formula I gave. So that's another example. Okay, so let's move on to a different kind of series called the telescoping series. There are lots of examples of telescoping series, but the one I want to start with is probably the first one you would encounter. This would be the sum, the sum, n goes from 1 to infinity, of 1 over n squared plus n. Now it doesn't look like much yet, but if I factor out the n on the bottom, you get 1 over n times n plus 1. Now 1 over n times n plus 1, you can do a partial fractions expansion, and I'll save you the algebra. There's 1 over n minus 1 over n plus 1. So this sum is the sum n goes from 1 to infinity of 1 over n minus 1 over n plus 1. It's nicest to write it this way because this sum, if we go down here, is equal, we'll just write out the first few terms, the nth partial sum. So the nth partial sum is 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4, etc., all the way up to and including 1 over n minus 1 over n plus 1. Now notice all the terms on the inside, they cancel. Everything's going to cancel except the first term, which is 1 over 1, and then minus 1 over n plus 1. So this is 1 minus 1 over n plus 1. Now what happens as n goes to infinity? As n goes to infinity, this term gets whittled away. It goes to 0. So therefore, the SNs approach 1. So therefore, the telescoping series, it has the summation 1 over n squared plus n goes from 1 to infinity, has the sum 1. Nice result. Okay. Okay, so I want to talk about one more example today, which is called the harmonic series. This is simply the series n goes from 1 to infinity of 1 over n. So it's 1 over 1 plus 1 over 2 plus 1 over 3, etc., plus 1 over 4. Okay, so now we're going to see that the question is whether it converges or not. So let's write down certain partial sums. I'm going to look at the partial sums of powers of 2. So S2, I want to compute a bound for S4, S8, and so on. So S2, that's 1 plus a half, adding the first two terms. S4 is 1 plus a half plus a third plus a quarter. Now I'm going to group the third plus a quarter together because that's going to be bigger than, strictly bigger than 1 plus a half plus a half. Let me write it as a quarter plus a quarter. And that sum here is 1 plus a half, so it's 1 plus 2 halves. Or let me write it as 1 plus 2 halves. Okay. What about S8? That's 1 plus a half plus a third plus a quarter. I'm going to group those like before. Then a fifth plus a sixth plus a seventh plus an eighth. And now this is strictly bigger than what? It's strictly than what? The first set of parentheses is bigger than a half. Because a third and a quarter is bigger than a quarter and a quarter. So this is greater than a half. And this is also greater than a half. So this is greater than 1 plus 3 halves. Well, you can see the pattern. The 2 to the nth partial sum of this series, the harmonic series, is bigger than, strictly bigger than, 1 plus n over 2. So as n goes to infinity, 1 plus n over 2 blows up. It goes to infinity. Therefore, that will imply that s sub 2 to the n goes to infinity. So in other words, the series diverges. That's what we just showed. Okay, I think that's enough for today. So that's all, folks.